So we will get started. This is the last thing for the day. And Richard's going to talk to us about upper air influences. So go ahead, Richard.
All right. Thanks, Tanya. Welcome back, everybody. This will be the last of the pure weather modules for the course. So yeah, going back up above ground for the most part here. So I'm gonna kind of jump in and out of the PowerPoint here. There's some links to some radar animations that I want to show, but I'll start out in the PowerPoint, get those started, probably jump to the web browser and then maybe back into the PowerPoint later. So pardon hopping around, but yeah, let's see how it goes here. All right, so we're calling this the third dimension of the fire environment, the upper air. So really up to about the tropopause, and we'll say approximately because things like strong thunderstorms or big fire plumes can actually deform the tropopause. So we do get some interaction with the stratosphere from time to time, but most of the weather takes place underneath the tropopause. We'll look briefly at fire and atmospheric interactions. You'll see a bit more of those this week in other modules. We'll look at basic storm safety, introduce some stability indexes, and there are a lot of them. Most are more applicable to shower or thunderstorm development, but also take a look at the Haynes Index, which was developed for fire. And we'll take a bit of a look at wind profiles and plumes. So, if we start at the bottom here, the fuels, of course, has a bit of a vertical component to it, of course, and we've talked about fuels quite a bit so far in the course, so we'll carry on, and there has been some introduction to topography as well and influences on fire, but then there's more just kind of pure atmosphere interactions with fire as well, so we'll take a look at those, and that's kind of the top of this little ladder here that we're looking at. So I'll start out with some storm safety and considerations. Just, I think most people are familiar with types of hazards from storms. Outflow gusts, well, you get a strong thunderstorm. You can get air sinking down to the surface and spreading out. That's what we call outflow. Some of those gusts may exceed 150 kilometers per hour. I've actually seen them up to probably 170 or maybe stronger in some rare cases. So they can really blast away. And you do have the outflow like that. It hits the ground and actually might rebound and start lifting the air above it. So some of these outflows may lead to new storm cells. So you always have to be aware around the edges of big storms, you might actually get some of these new cells popping up just due to that outflow spreading out and lifting up the air. And of course, tornado is another form of wind that are pretty localized but very devastating. And some of you might have seen paths in the forest where tornadoes have come through. They can tear down a lot of trees, and they usually have a bit of a rotation pattern visible the way the trees fall. But then you've gone from a standing tree type to more of a slash type. So, of course, those paths will be fairly small usually, but definitely change the nature of the fuels. Precipitation, besides heavy rain, of course, we can get large hail, which can be dangerous if it gets big enough. Heavy rain, of course, can cause other types of problems like washing out escape routes and things like that, creating erosion, resulting in slides. So all sorts of potential problems there. We'll talk a little bit about heat bursts and pyrocumulonimbus clouds later in the presentation, and kind of emphasize crew safety due to storms and fire spread as well, since all of these can play a part in keeping safe out there in the bush. So I'm not going to go through this entire thunderstorm comparison chart, but pick out a few highlights of it. So the top row there, we call the environment. What type of atmospheric conditions do they occur in? And across the top, we've got the different sizes or forms of thunder showers. So single cell, multi-cell, supercell, or squall line. So 4 of them that we've got listed. So the single cells, fairly weak or moderate instability. If you get the stronger instability, we might get the multicell or supercell. And supercells usually occur along the jet stream, usually to the south of a fairly major low pressure area. And then, of course, the squall line, frontal passage or trough. It's a fairly long line. We'll talk about that a little bit later here. Single cells usually, they can pop up, within 20 or 30 minutes and rarely last more than an hour, but you can get clusters of those and, we turn into a multi-cell storm sometimes. So one cell will die off and something else is popping up, so they can continue for quite a long time. The squall lines, of course, with the frontal passage may last between hours or even to days if you have a fairly strong cold front passing through a large portion of the country. That line of thunderstorms may stay active during the day, overnight, into the next day, and that can continue for a few days sometimes. Movement, usually with single cell, just kind of follows the upper wind flow, and it's always something to be aware of is if you're looking at lower clouds, the thunderstorms may not always move with the lower cloud direction. They can quite often cross, and the upper winds will be blowing from a slightly different angle. So mostly thunder showers will tend to follow those upper winds once they get well developed. And the multicells may be erratic with a lot of kind of comings and goings of cells, some stronger, some weaker. Supercells can move right or left of the upper airflow, and they'll actually take a look at a radar image of a splitting thunderstorm, which is another trick they can pull on you. Precipitation is quite varied, but usually with the supercells, you get the largest hail and heaviest rain. They can last for hours. They actually generate their own kind of weather systems, and just like a very small low pressure area just wrapped up in that storm. With those, the anvil tends to overshoot the top, so you can kind of see the typical anvil that it turns into kind of a serious cloud, but you quite often see that cauliflower-like cumulus phase shooting up over top of those. And wind, of course, fairly erratic or strong gusts in multi-cells for sure, and supercells are more likely to cause a strong gust fronts and possibly tornadoes. The frontal passages, you might get a very brief burst of wind, where it might last for an hour or a few hours, and other situations might last for quite a few hours or even a day or two after the frontal passage. Just down at the very bottom there, the extent, the single cells just cover a small area, but the multi-cells could cover a large area, and that MCC is a mesoscale convective complex, just usually a large, fairly roundish cluster of thunderstorms just driven by a fairly warm, moist air mass. And quite often see those usually in the moister areas. You get them in the States quite often, but we have seen them in places like southern Manitoba, maybe Ontario from time to time. Once you get further east in the prairies and into eastern Canada, usually in a moister type of climate pattern, so maybe the MCCs are a bit more common out there. Last year, though, we did see some of those coming off the Rockies in Montana and drifting northeast, so eventually, I think, moved through parts of Saskatchewan and Manitoba. Now, the title of this, it's one of my pet peeves, lightning. There's no E in the word. I quite often see people spell lightning with an E, and of course, that's got a completely different meaning. Lightning with an E means to get lighter, either in weight or in shade, I guess, but the lightning, the electrical phenomena, does not have an E in it. Another common thing is to miss that first N, so we end up with lighting, so it can be a tricky word to type, so just always double check if you have to type that word. Environment and Climate Change Canada's motto, thunderstorm motto, is when thunder roars, go indoors, and the reason for that is if you can hear thunder, you're probably within range of positive lightning strikes hitting outside the main storm area. And if you just look at the diagram here, I'm just going to fire up the highlighter again. And we do have the anvil with positive charge up there, and positive strikes will quite often hit outside that rain shaft area. They do carry a stronger current as well, so they're more likely to start fires and they're more likely to be dangerous to lives. So those are the worst kind of lightning strikes to be in proximity to. The negative polarity ones, starting usually the center of the cloud, you've got the -15 degree level here where you start to get ice particles forming in the cloud, and ice tends to lose electrons more readily than water, so you get that charge separation happening in the cloud. But most of those negative strikes will just come out of that rain shaft area. Of course, they can all be dangerous. There is quite a range in strengths of these discharges, but yeah, just something to always be aware of is how close you are to lightning strikes. And positive polarity strikes, I guess, just at the bottom there, talked about the anvil to ground discharge. More common in the winter and higher elevations, and of course, you're probably not out there fighting fire too often in the winter, and thunderstorms in general are a little less common in the winter, but maybe if you move to further southern latitudes, maybe it's a bit more of a problem down there. All right, and radar allows the speed estimates of storm cells, but here we're going to see some of the tricks that they can play. So I'm just going to jump out of the presentation here, and excuse me for a second. Get out of there. I'm just going to reshare the screen with the browser up. All right, so I won't be able to draw on this, but we're looking at thunderstorms in southern Manitoba here, southwestern Manitoba. So the one to pay attention to is right at the bottom, the area where you've got those bright reds and purples down there. So I'll just animate this a little bit, and I think I'll slow it down. Just at that point there, you can actually see the storm actually splitting in two. Just play this through again once or twice. So you can start to see it taking a butterfly shape, then it splits. So with some of those strong thunderstorms, you can get strong inflows on both the north and south sides of it. So it starts actually tugging away at the storm, and you can get it separating into two pieces. And quite often that southern cell has got the warmest and most moist inflow, so it tends to stay the strongest. But both sides can be fairly strong, as in this case. So if you compared that to the upper winds, well, you'd have that. If you have the wind on your back, the left one, would tend to move off to the northeast, and the right one usually to the southeast. So, fairly important tool, radar is to just help let you know that these things are going on here. By the way, these are the old X-band radar images. If you look at Environment and Climate Change Canada's radar now, it's got a completely different presentation. So the echoes will still look similar, the color schemes, but the background and everything has changed. All right, so just back out of there. Look at the next one here. So just an example of some erratic movement, some quick development. So we've got a fairly good cluster of thunder showers here. I'm just going to slow it down again. All right, so you should be seeing cluster of thunder showers around the Edmonton area. Is that coming through okay? Everybody seeing the Edmonton area? Yep, okay, there's some thumbs up. All right, good. All right. So we just look just on the the west side of Edmonton. It's got the little dot just to the on the right-hand side of that innermost circle. Get a good patch developing right there, so it kind of goes from patch of cumulus clouds up to a fairly intense thunder shower. And once we get those red shades in the radar echo, then it's probably generating some hail. So, a lot of these things can pop up within 20 or 30 minutes and, go from mostly nothing to a fairly intense shower quite rapidly. I've actually seen a supercell develop in about that same period of time, just going from a puffy towering cumulus up to a raging supercell with its own kind of weather circulation embedded inside it, with well under an hour of development. So they can change quite rapidly. Quite often when you get these big clusters of thunder showers too, you get these multi-cell storms, and stronger cells kind of suck in the weaker ones, so you might get really erratic directions in there. The big ones might maintain a fairly consistent direction, but quite often those weaker cells will get pulled around a lot, and yeah, so you can always have to watch them to see where they're going. All right, just going to jump back into the PowerPoint. And all right, so I've gone through those. Oops. Don't expect you to memorize this or anything like that. I just once tried to figure out how far, where you could see a storm top from. And, if you imagine the Earth as being billiard ball flat, then this type of equation would somewhat work, I guess. So, this estimate comes out at just under 450 kilometers away, assuming the top of the cloud is about 15,000 meters above the surface. So it'd probably represent a reasonably strong thunderstorm. If you're, it's rare that you'd actually be able to see that far because you've got trees and hills and buildings and things in the way. But if you're in a tower, for example, that small h just at the top right of the diagram there, it had your height of the tower and the height that you are, or eye level, and you could adjust that little h a little bit to come out with maybe representative height of your observing platform. Just going to back up, I guess, just on the speaker notes, if anybody happens to look at them. The one time I was driving from Edmonton to Calgary, which is about 300 kilometers, and you could see a cumulonimbus top in the distance there quite easily, and that's about 300 kilometers away. So, yeah, maybe the 440 is not too bad of an estimate if you've got a really flat surface that you're looking at or across. Warning services, Environment and Climate Change Canada has their WeatherCan app, and of course their webpage. They've got the combined warnings and watches with the radar on an interactive map now, so you can look at all of those things on the same map and kind of toggle on and off each one. With the WeatherCan app, you can kind of customize the regions that you get alerts for as well, and they're working on developing these alerts and warnings for 10,000 individual locations across country. So getting fairly granular. I think I mentioned that probably last week during one of the weather presentations as well. Maybe your own fire weather office might provide a service as well that alerts you to storm danger or anything else like that. Well, some of the things that happen with thunderstorms besides precipitation and winds is the heat burst. So if you get the right conditions in a fairly strong and dissipating thunderstorm has kind of reached its mature stage, you can get these big downdrafts that form in fairly dry upper levels, and they'll sink and heat, and due to adiabatic compression, so there is sinking and heating. And by the time it reaches the surface, well, you get an outflow wind, but you might also get a a rise in temperature along with it. So I think I've really just kind of mentioned that. Well, with temperature increase, of course, you're going to get the humidity drop as well, assuming the dew point doesn't change much. So a couple of examples of those, Springbank Airport, just west of Calgary, Friday, August 7th, 2001. So you can see the temperature just kind of going into the overnight period is, really, I think pretty reasonable for the time of year, kind of a summer day. You're in the low 20s heading into late evening, but we've got this jump at 11 o'clock local time there up to 25 degrees. And if you look at the weather comments on the right-hand side, we've kind of gone from smoke to lightning in the southwest. That's the LTG is lightning, and the direction SW southwest. By the time it gets up to 25 degrees, an hour later, we've got CB reported in the south of the station location. And you can see the wind starting to shift around a little bit too, so not a huge amount of difference in direction, but you can see the wind speed pick up, so up to 48 kilometers per hour and then 60 gusting to 100. So get an outflow there somewhere at around 11 o'clock or a little bit after. They did report a rain shower, and maybe the lightning activity had stopped by that point. If it was an active thunder shower still, it'd have a T in it, TRW. But yeah, the temperature jumps up midnight. It's still sitting at 26 degrees. Then by 1 a.m. it dropped down to 19. So just continued on its merry overnight type of trend by that point. Glasgow, Montana, at the bottom here, temperature jumped 15 degrees Celsius just in a few minutes there. So really rapid increase in temperature. And what would the RH do? Well, if dew point depression was 10 degrees, RH 50% to start, well, you're kind of doubling that and then half again. So, you're going to come down to 25, you're going to come down to about 18, probably 18% or so, a little bit under 20%. So, yeah, quite a rapid rise in temperature and big drop, big drop in RH at the same time. Don't have any wind information from that storm here. So, yeah, with the heat burst, well, and the thunderstorm downdraft, what really starts it, you get these really strong thunderstorms and they push up into the tropopause, which I think has got some elasticity associated with it. You've got warm air above that. It's very stable. So if you get a big push up into it, well, it's probably eventually going to be springing back down. And there's a paper that describes kind of short-term oscillations up around that tropopause there, maybe in the probably an hour or so, maybe not much longer lived than that, but might be enough to kind of initiate the big downdrafts that come down. And when we talk about big fire plumes, well, you get a plume collapse sometimes too, which may be quite similar in physical actions there. The plumes can push up into the troposphere as well, and maybe we get that same type of gravity wave oscillation occurring, which might help kind of drive the air back down towards the surface. Of course, with all that happening, the changes in fire behavior can be quite dramatic. So, you've got, besides changes in temperature and RH, well, you've got strong winds. You might change direction, might be quite erratic for a while as the thunderstorm passes. As you get around to the side or the back end of it, the wind direction will probably change. We'll talk a bit more about collapsing plumes a bit later. But first, let's go into some stability indexes. So I mentioned before, most of these are for shower thunderstorm storm development. But once again, what is the real interest? Are you trying to predict weak or strong thunderstorms? I think most public forecasts will tend to focus on storms of the stronger side, but if you're interested in fire starts, maybe the weak ones are just or maybe even more important. You get maybe a little bit of rain, some lightning for a while, and maybe the shower dissipates after that. So the weak ones, of course, can start fires for sure. So most of these use a combination of upper air temperature, humidity, and wind, but on the thermodynamic diagram, there are more complex stability indexes as well, the lifted index and CAPE. Most of the other ones before that just use fairly standard levels, so things like 850 hectopascal temperature, or winds at 500 versus winds a bit lower down. So kind of a combination of fairly standard information, but the lifted indexes and CAPE are much more complex since we're trying to calculate energy levels in the entire portion of the atmosphere where that air particle can rise to. Now, for fire purposes specifically, the Haines Index was developed in the 1980s in the US, Donald Haines, and they just have two components, sorry for stumbling, stability and dryness, or moisture. So we've got, once again, standard levels, 850 hectopascal temperature and dew point. So there's our moisture dryness factor there, and then the 700 hectopascal temperature. So the difference in temperatures between those two levels will give us that stability component. So they're kind of standard levels, but if you're very close to sea level, maybe you can actually use the 950 and 850 hectopascal level. And in the, or as close as you can get anyways, in a radiosonde report, there are what we call mandatory levels. Those are always reported, even if they're actually below ground level. In that case, they're just coded with missing data. But if those atmospheric levels are above the surface, they will be reported and they will have values. So I think they start at about 950 or 925 or 1,000 even, 1,000. 950 or 925, 850, 700, 500, 250, and so on. There are a lot of other levels that are reported in between those, but all of these stability indexes really depend on use of those mandatory levels, so we should always be able to get those in a standard radiosonde report. Up in higher elevations, instead of using the 850 and 700, well, we can move up a notch and go to the 700 and 500 hectopascal levels. All right, so on the left, stability factor, difference in temperatures between the 850 and 700. So if you're going to have an unstable atmosphere, well, it's probably going to be warmer down below. So you'll end up with a positive value for that stability factor. And you can give it a ranking just based on the temperature difference between those two levels. So greater than 11 degrees, you give it that higher ranking of 3. Dryness factor on the right, looking at the 850 millibar or hectopascal level there, just the dew point depression. And once again, the bigger value gives more indication of dryness, so we give it a higher ranking. Then you just add those together. So, I guess the most critical, of course, for fire behavior would be something in that 5 or 6 category. The upper range of the Haines index there. Anything underneath 3, I mean, it's, we can only get a ranking of 2 or higher, but 2 or 3 is pretty low, so I wouldn't worry about anything down that low, really. But, if you look at a kind of a climatology of Haines index, it's just for Stony Plain, west of Edmonton here, about a dozen years in this particular study. Well, the 6s occurred about 20% of the times, and 5s about 42% of the time. So, really, we're getting almost 2/3 of the Haines index calculation there, sitting in the moderate to high range, and not many that actually come out with a value of 2. So, it's pretty common to get a lot of Haines index up at the top of the scale. So the Australians tried it out and they thought, well, this isn't very useful. We're always getting 6s. So what can we do to kind of stretch out the scale a bit. So they did kind of rework the formula a bit. Got a maximum value of 13. It is a decimal. There's no lower bound, but once it gets below a certain point, well, stable is stable is stable. So from a fire perspective, if you get a low value, it doesn't matter if it's, +2 or -6 or something, it still indicates extreme stability. So, really you're concerned with values in the upper part of the scale there, but with this reworking, we shouldn't get too many that are maxing out. They probably should be in the mid-range, and this might be on the next slide, but I think a value of 9 or so and higher is kind of indicative of maybe severe fire activity likely. So yeah, kind of a very similar concept. We're still using those pressure levels. They've just reworked the formula a little bit and still summing the stability and moisture classes together. So it all works the same way, just a slightly more complicated equation. And we'll jump into wind profiles for a bit. It's got an older origin than the Haynes Index. The George Byram's blow-up conditions, well, it was first described in the 1950s, so quite a long time ago. Tend to, really focus on maybe low-level jet occurring, fairly moderate to strong surface wind, maybe a low-level jet, and then kind of a decreasing wind as you get up to a certain point in the atmosphere, then increasing again. But let's just carry on to the next slide here. So Byram identified about half a dozen profiles here. There's actually 7, but I've got kind of A's and B's and C's listed. So 7 of them. Usually the lower numbers are more indicative of severe fire activity being likely. So 1A, fairly good surface wind. These are in miles per hour, so a little bit of a conversion to get to kilometers per hour. But fairly moderate breeze at the surface, and then it kind of tapers off a bit and increases again once you get up into that over 6,000 feet, a couple thousand meters up above the surface and higher. 2A and 2B both have that low-level jet, increasing wind a little bit above the surface here. Similar in 3A and 3B, but you can have an even stronger low-level jet in 3C, but then the profile, the shape of the profile above that is a little bit sharper, kind of decreases more rapidly and then increases again more rapidly. 4A here is kind of an interesting one, just kind of a steady increase as you go up. And if you remember that Saquet fire plume last week, I had a kind of a similar profile, at least, through the lower levels of the atmosphere too. Type 4A here, just reasonably steady increase. 4B and 4C, well, we've got pretty steady winds. There may be a bit of variation right at the surface, but once you get up above the surface, it really stays pretty steady as you go up through the atmosphere. From Environment Canada, Erhard Reinhold in 1989 did a bit of a study. It wasn't really a rigorous study. Found that 10% of the profiles that he looked at fit Byram's classification, so not many of them. So there's probably all sorts of other variations in wind profiles that you can get out of soundings. Only 3% matched Byram's surface wind speed, so even fewer just matched that kind of moderate surface wind, and less than 1% being type 1A, so a very small amount. I guess, one of the things Byram did a lot of his wind profiles in the southeastern US, so we do have kind of different jet stream characteristics between southeastern US and a lot of Canada, so it's one thing to keep in mind, might help explain some differences in the types of wind profiles seen. In the Reinhold study, they used 20 years of data, didn't specify which years, didn't specify which years used the true radiosondes or the smaller variation, the pi balls. You know, is the piebald wind data good? I mean, we've launched a few of those, and sometimes you get good data, sometimes you get some pretty wonky data. So, you know, we didn't know if any of them were rejected just because they looked weird. So, yeah, kind of a non-rigorous study. 1977, the Sprotec and Rafe Snyder profile, very similar, I guess. If you back up, it looks a lot like the Byram 4A. Just they've got pretty much a straight line here, but kind of a similar type of increasing wind as you go up. And if you look at the height scale, that goes up to about 10,000 feet, so 3,000 meters, roughly. So once again, we're just looking at the, basically the lower part of the troposphere here. All right, so just a few details here. Once again, Eastern USA, 52 fires, a 10-year period, looking at large fires there, 5,000 acres here. Bigger, about a third of those had low-level jet. That's what that LLJ is right there. And the way they defined the low-level jet was a change in wind speed over 300-meter height increase was greater than or equal to 2.2 meters per second. A lot of those occurred in prefrontal jet streams, so we get a cold front or maybe a warm front followed by a cold front coming through, and as that low pressure area moves into your area, well, you get that prefrontal jet stream, usually at low levels. Yeah, it's kind of similar to Byram's 4A, but yeah, maybe a bit of a contradiction. Byram has a bit more wiggles in the line, and this one's pretty straight. So, I don't quite know how they, it's probably just a regression line, I think, in this case, where they're trying to estimate the best fit amongst a plot of different points. Lower level jet example from Calgary, 1990, about this time of year, autumn. You can get some pretty strong Chinook winds coming across the Rockies. YYC, of course, is Calgary Airport code. Something that I find a little odd about this is, the elevation of the Calgary Airport is close to 3,500 feet. But if you look at this plot here, the YC right there is just a little bit over 2,000. So, something's wrong here. So I don't know if they've plotted the airport level at the wrong elevation here or what, but and of course the wind profile starts down there too. So maybe this whole diagram should be shifted up the plot a little bit. I'm not really sure, but really the important thing is that we've got a pretty good surface wind speed here. It's kilometers per hour, so we're probably up around in the 40s somewhere, but as you go up, you get this extremely strong wind speed up above, and it's probably up to 160 or 170 kilometers per hour up there. So extremely strong. If you get any instability with that and mixing it down, of course, then you can get really strong and gusty surface wind speeds. Yeah, just at the bottom there, just popped up another little box. And forgot to ask the question, which Byram profiles may this fit? Well, looks like anything between about 2A and 3C. We're not looking at a very deep portion of the atmosphere, so we can just really compare it to the lower part of those profiles. All right. We've talked a little bit about the value of vertical profiles earlier in the weather modules as well, and certainly showed plenty of these University of Wyoming thermodynamic diagrams. So we've talked a bit about this already. Inversion breakdown, of course, leading to increased fire intensity. Air mass stability assessment, showers or fire behavior, we've talked about that a bit. Wind, I've kind of gone over a little bit of that already, and of course, with any mixing, inversion breaking, then you can get that wind or drier air mixing down to the surface. So it all helps determine if you might get just strictly a wind or a plume-driven fire. So with wind-dominated fires, well, it's it's the wind energy that's driving them. In this particular example, it's in a valley, so we've got a bit of upslope flow as well. That's probably helping out a bit, but looks like a pretty good wind blowing from the left to right. Don't know which location this is or what direction we're facing. You can probably see just in the background at the left, maybe there's some higher hills in the background, maybe with some forest cover on them. But yeah, I get that strong wind at the surface, wind speed up higher, up above the ground, maybe high, or maybe there's a stable layer present, and can't really see for sure, but maybe there's a hint that some of the smoke's getting caught up at a certain level just on the upper right part of the diagram there. Really hard to tell with this particular photograph. So here we tend to focus on smoke plumes rather than the convection columns that pretty much go straight up in the air and start to develop their own weather phenomena. So besides the wind driving things along, well, we've talked about heating of fuels before, but also when you have a wind, if you're not familiar with the term advection, I think I've probably mentioned it before. That's just the transport of some parameter, through wind or some other means. So it might be moisture advection, or in this case, heat advection. Get the wind blowing the heat along, and it might tend to heat up and dry out the fuels ahead of it. So it's just another process that happens, besides radiation or convection and things like that. Now, if we get into a plume-dominated fire, well, then we've got these huge towering columns that look like cumulonimbus clouds, and of course they can form CBs up there, so a lot of similarities. Sorry, mouse has just gone a little crazy. Just trying to erase the ink again. All right. So yeah, with the kind of like a thunderstorm, you get that certain amount of energy going into the column, and you'll attain that level of free convection. The air is kind of free to rise up and many thousands of meters high. So you tend to get very intense burning and rapid spread rates. Surface winds are usually kind of a moderate strength with lighter winds aloft, and you can see this column pretty much going straight up there. Unstable air mass for sure. You need a good unstable air mass to get these things to develop. And of course, if you've got a heavy dry fuel load, well, you're getting much more heating just due to fuel consumption going into these things. Yeah, so strong and erratic winds are one of the main consequences of those. Just kind of like the thunderstorm collapse, so you might get smoke plume collapsing as well, and then you can get kind of outflow winds and dry air getting mixed down, possibly temperature increases and things like that. And you get all this kind of churning around, and you can get this huge amount of radiative heat as these fuels tend to increase their burn rate, and then you get that radiative heat transfer to dry fuels around the edge of the fire. So it just becomes kind of a self-feeding type of phenomena. So related to that, we've got our pyro-CBs, or if you prefer the Latin term, the cumulonimbus flammagenitus, or flammagenitis, however you want to pronounce that last part of it there. Got some examples from British Columbia again here on the left. So had some pyro activity there, and very strong plumes and pyro-CBs that developed. And just on the bottom right here, you can see kind of the result of that with a lot of lightning strikes up to the north of this. This is just northwest of Kamloops, and kind of stretching up, I guess, close to Quesnel, a little bit to the southeast of Quesnel, but it can be a fairly long-lasting phenomena too, these pyro-CBs. So get some pretty strong development out of these bigger plumes. So a lot of lightning came out of that. I think some hail and some new fire starts. Just the photo on the right there, just another example of a type of situation that you might see. Very strong, kind of vertically oriented plume. Some of those may produce not too much rain, others may produce some fairly heavy precipitation and and hail on things. Definitely lightning and winds are, some of the primary hazards out of that. We've even seen a bit of a kind of a weak pyro CB out of grass fires sometimes can get a fairly heavy grass load and intense burning, and I've actually seen kind of muddy raindrops come out of some of those smoke plumes before. So it's not as intense as what you'd get in the fairly heavy forest burning, but it still appears to be possible out of grass fires too, but probably quite rare, I think. A lot of the grass fires, I think, tend to be quite wind-driven, so instead of having a big towering plume, you'll just get, or a column, you'll get kind of a long plume stretching out ahead of the fire. Byram's convection number, so we'll go into a little bit of this. It looks like a pretty simple equation here. Just the power of the wind or the power of the fire over the power of the wind, just a strict ratio. But we'll see the details here shortly. So NC, Byram's convection number less than 2, kind of a wind-driven fire. No convection column really present. If you get up to 10 or higher, then you've probably got a plume-driven fire, and you get that convection entraining air from the sides. Helps create a bit of instability in that column. So once again, I guess similar to the extended Haynes index, you get numbers up around that 9 or 10, and once again, it probably indicates fairly severe fire behavior could be present. But, if we start to expand this a little bit, well, we get into a little bit more of a complex looking equation here, and I'm not going to go through all of it. You can kind of look at all of the variables that go into this thing, and we'll go into the next slide, but just at the bottom, it's Byram's convection number is usually calculated at the surface and then maybe a few other levels up above. So once again, you probably need a bit of wind information and things like that above the surface. Then if we fully expand it, well, right at the bottom here, you can see what it turns into. So it, becomes quite a complex equation and starts looking like a kind of a fancy building with terraces and an underground parking garage or something like that. When you get into these fairly complex equations, just at the top right, kind of an analysis of units can kind of help determine if you've got it laid out correctly. And in this case, we're doing a strict power ratio, so it should come out dimensionless, no units. So all of these things should cancel out if it's laid out properly. I guess some of the pitfalls here is I guess we don't go into it. Go into it on the next slide. Got to be careful using the rate of spread out of the FBP equation that you get all of the right coefficients for the particular field type that you're looking at, and it's probably one of the one potential traps in this is just getting those right numbers for that particular field type here, or your best estimate of it, I guess. So in this case, we're looking at a C3 field type, moderately high FFMC, is just kind of getting into that extreme range at 93. BOI not too alarming, but still, getting up reasonably high there. Surface wind 20 kilometers per hour, surface temperature 18. We've got a few other given things here, like the crown fraction burned and fuel load are given here, so you don't have to work through all of the FBP equations in this particular example to come out with that. But if you're starting from scratch, you'd probably want to have those things calculated for your location. So in this example, we're doing surface, and then we're going up to 300 meters, where the wind is 35 kilometers per hour, so just about doubles in that 300-meter ascent. So in this particular example, we come out with just under a 6 at the surface. So, once again, it's not really indicative of, really strong plume-dominated conditions. And up a little bit higher, well, it looks pretty tame up there, getting a value of 1 at 300 meters. So maybe no real intense strong plume developing out of this particular scenario here. You know, I used to give this, well, at one time I gave it out as an assignment to work through this calculation. And, you know, when I first started doing this, I got different answers than the previous instructors had. So I worked through it twice, came out with different answers twice, threw it back at the students 1 year to work through to see if they came out with the same thing that I did. And, you know, some of them, I think about half of them came out with the same answer and half didn't. So a lot of potential pitfalls in a fairly complex equation like this. But this part is not an assignment this year. You know, worked through it again and came out with this roughly 5.8 at the surface, and about 1 at 300 meters. So they're kind of stabilized on that answer. But yeah, I won't torture you with going through all those calculations this year. But something that I do want you to do, and I must apologize for this. If you look at the binder notes, I think just on this slide it says this isn't an assignment, but it actually is listed as an assignment. So yeah, please do this reading. There's a few questions to answer, 3 questions down there. I think we've got these papers sitting on Canvas. If you have any problems locating them, let us know. And with these scientific papers, you know, we don't expect you to go through all of the procedure, you know, in fine detail. We can probably just read the introduction and maybe the discussion and conclusions to come up with kind of suitable answers for these questions. And we don't want you spending, you know, 6 hours trying to read the fine details of all these things. All right, so just in summary, you're looking at atmospheric phenomena, and, you know, probably just kind of touching a few details here, and there's probably a lot more that people could go into with time and other types of studies and things. Fire can influence the atmosphere can influence fire, and it is a couple of fairly complex physical processes. And when they can influence each other, it does make it even more complex. There are people that have developed kind of fire atmospheric interaction models, but you know, once again, they're very CPU intensive, and takes a lot to process all this data. So tend to be on fairly fine scales for short periods and can still take an awful long time to run. Anyways, crew safety, of course, depends on weather and fire factors. We've talked about a few of those, and you'll hear some more later this week as well. A downdraft from thunderstorm or collapsing plume can cause erratic fire behavior, maybe heat bursts and other things. With the erratic fire behavior, you always tend to get kind of an unstable column. You get air mixing in from the sides. You can get that plume collapse. You can get outflow, all sorts of interesting things, and of course a lot of radiative heat that just keeps that fire going. Vertical atmospheric profiles help determine likelihood of showers and thunder showers. Some might be better at predicting kind of the weak events, and others may be at the higher end of the thunderstorm scale, the kind of the supercell type event. So, you know, really there are kind of keys for interpreting a lot of those stability indexes. So you really have to keep in mind, I guess, what you're looking for if you try to interpret those. You can also give you clues into the blow-up potential. We've talked a little bit about that, and the likelihood of plume-driven fires. So with that, we'll just go to the contact information and then turn it back over to everybody there, see if there's any questions or discussion.
There's a question in the chat, Richard, because this exercise is new.
Yep.
Only part of the exercise. So when is this due?
I thought we had it in the Canvas list there. Just a second. I was a little confused about that myself since I didn't realize that we actually had it in there. I would think. Yeah, we've got it
Oh, actually, no,
marked on.
I stand corrected. It's listed for the 28th, so it is in
Yeah,
there.
it is in there. Do you want more time for that? I don't know what the week after looks like, but you know,
Week after is the final exam, so.
it's final exam. I mean, yeah, I mean the Friday, the 29th, I think is still fine as well. So, you know, wouldn't sweat too much trying to get it done on Thursday.
Richard, can you see the chat? Kim has a question for you there.
Yep, I can look at sorry, popped it up. All right. Yeah, and downdraft and column collapse, you know, it's I don't know if I can really come out with any significant differences between those. You know, the mechanism for having them happen might be quite similar. You get this this big updraft that pushes up against the tropopause. It tends to be a bit spongy. You've got warm air up above that, so tropopause doesn't want to move upwards, but sometimes it can be forced up. So you've got these competing forces. You've got that buoyancy from below and gravity and stable air above trying to push things down again. And you know, I don't know if there's any real significant difference between a thunderstorm downdraft and a fire column collapse. You'd really have to, I think, investigate that much more thoroughly to give a complete answer to that. And maybe we don't know it yet. You know, I've seen, you know, one paper that describes these kind of oscillations up around the tropopause, but there might be more out there. I guess, you know, maybe if there's one difference in the result, it might be the column collapse may not have precipitation associated with it nearby. Thunderstorm, you've probably got some fairly heavy precipitation in the vicinity. Maybe it's passed already, or maybe it's off to the side. But yeah, you can get a pyro CB, and you might get a similar type of thing with precipitation a little bit farther out from where the fire is actually located. But yeah, it's a lot of these things need definitely further research. Anything else?
Anything else for Richard?
Well,
Going
thank you,
once.
Stefana. Thanks for the thanks.
Going twice.
Yeah.
All right, so this session was supposed to run until 2:30, so we're going to cut you loose early. Just a couple of reminders. You have 3 pieces due tomorrow: the histogram and the atmospheric stability assignments and the venting discussion. They're all due for tomorrow at 11 Mountain. And tomorrow is a shorter day. We only have 1 session. We're looking at spot fire occurrence prediction with Dustin from Parks Canada from 10 to 12:30. So with that, you guys can be cut loose.
Yeah. Guess our next office hours is Wednesday by the look of it too. So yeah. So all right. So yeah, you'll have a bit of time over the next day or so to, I guess, do what you need to do.
And the final exam is next Monday, December the 2nd. It's got a 3-hour time slot. but you only have 2 hours to do it. So we left you a little bit of flexibility there in terms of when you want to start, but once you started, you've started. And it is a firm 2-hour deadline. We have covered a bunch of stuff over the last week, and we still have a couple more sessions to go, but it might be worthwhile trying to put together some notes thinking about the final exam, because already 2 weeks ago seems like a long time. The format on Canvas, a lot like the quizzes. Any other questions, comments? We'll talk more about the final as we get closer to the end of the week, but just wanted to flag that for folks to make sure that you have some time. Yes, you will have access to your tools. So the typical stuff, right? Like it's your sort of no Googling stuff, but any of your FBAN tools are fair game. All right. Have a good one. We'll see you guys tomorrow at 10 o'clock.
Right. See y'all later.